Today's first talk by Julian Chaidez, okay, thank you, from UC Berkeley, and his talk is on a Legendrian A infinity category for contact manifolds.
Cool. Is this thing on? Oh, yeah. Okay. Thank you for inviting me to the organizers. I'm really happy to be here. All right, so today I'm going to talk about what the title is, so an infinity category of Legendrians. So I really like agendas. I think they're kind of puerile, but also they're pretty helpful for knowing what's happening. So first I'm going to talk about goal of the talk, motivation for why this is an interesting thing to do. Then I'm going to give a review of the Legendrian DGA, so which will be helpful for people who don't remember it or haven't seen it before. I'll talk about how to construct the infinity operations. So this will be like kind of a sequence of pictures along with algebraic operations that kind of correspond to them. And then I'll talk about some how to construct the category involving these operations. And then I will talk about some kind of applications of this category, which are kind of in the spirit of the thing that you would kind of ideally use this kind of technology for. Okay, and this is work in progress, so it's kind of a little bit, it's not written. It's not like it's kind of like 50% written up at this point. So sorry if there are some things that are not totally clear. Presentation isn't totally set yet. But basically, it's a combination. So for the most part, the thing I'm going to talk about today is a combination of kind of this augmentations or sheaves paper by Ng, Rutherford, Chaidez, Sivek, and Saslow. And then a lot of the kind of treatment of the Rapfukai category that you'll find in like Ganatra-parted Chaidez. Okay, so the goal is I want to explain. Yeah. Yeah. Sorry, I'm not used to giving talks in such a huge place. So, okay. How much bigger? Like, is that? Okay. So I want to explain how to associate. So a pair of a contact manifold and an augmentation on the contact manifold. Which maybe just an equivalence class of an augmentation, which is really the only thing that's well defined. So this guy is a contact manifold. This guy is an augmentation. And to this thing, I want to explain how to associate some category, which I'll denote like this. Roughly speaking, the category is going to be the following kind of thing. So the objects are roughly pairs of a Legendrian and an augmentation on that Legendrian, subject to the condition that the restriction of this augmentation to the sort of orbit subalgebra of the Legendrian DGA, and I'll digest this later and kind of repeat this condition, but subject to the condition that basically the augmentation restricts on the orbit part of the contact DGA to the augmentation that you fixed for the contact manifold, and then the morphisms count curves in that already existed in the Legendrian DGA. So basically the construction is not really introducing any new holomorphic curve stuff. It's kind of just a repackaging of a lot of information from the usual Legendrian DGA. So then with that in mind, you could kind of ask, like, why is this an interesting thing? Or why is this something you might want to think about? So why is this cool or useful? Potentially. Okay, so one is maybe you're interested in applications to dynamics. So here the kind of one guiding question is, can the structure of this object, like this is kind of the standard question you would ask about any kind of floor theory of this setting, but can it tell us about dynamics questions for example, the Cord conjecture. So I'll remind you what the Cord conjecture is, because it's actually not, when I say the Cord conjecture, sometimes people don't know what I mean. So the Cord conjecture is that every closed, it's very simple conjecture, it's just that every closed Legendrian so lambda in a closed contact manifold Y has a Rabe chord. And there's a little bit of a stronger version of it, but maybe I'll just leave it at that. Okay, and then also, so this is like an example of kind of a very basic dynamical question about Legendrians that people are interested in. This is an open problem in dimensions higher than 3. So in dimension 3, you can prove it with ECH. So Michael Hutchings has a paper about that. But even then, the dimension 3 result is also not great, because actually it only says that there's a single chord. So so you'd kind of also maybe want sort of enumerative enhancements. So meaning things where you have some statement about, like, if this condition is satisfied, then you have a lot of orbits, or maybe some lower bound for the number of orbits. So you want maybe like counts, asymptotic stuff. There's all kinds of questions in this kind of vein which are interesting and at this point pretty difficult to access. So why? So you could have asked this question for the original Legendrian DGA. So why might it be useful to have the this category thing? So another reason why it might be a cool idea to have a category like this around is because because it kind of gives you more algebraic methods. So you can kind of try to port or adapt the method, these sort of powerful methods in homological algebra developed for the Fukaya category to study Legendrians, even Legendrians without fillings. So, so for instance, and there are lots of questions you could ask that are kind of structural questions about this kind of category. So for instance, and all of them, have basically corresponding questions in wrapped floor theory and wrapped the wrapped Fukaya category and for the regular Fukaya category. So for instance, you can ask about generation. You can ask about what is the relation of this thing, cyclic homology, with contact homology. It's an interesting kind of question. You could ask, does this thing have any Cauchy properties? So that's a particularly cool question, because maybe it would help with the kind of problem of calculating these invariants and then there are lots of other kinds of questions in this direction. Okay, and then maybe the last one, which I'll mention, is just that obviously, kind of what is the mirror symmetry? Are there any connections of this thing with mirror symmetry? I don't know the answer to that question, but I think it's a cool thing to think about. So interesting connections here. Okay, so these are kind of the reasons why I think it's an interesting thing. This is an interesting thing to try to do. Okay, and then I'm going to give a disclaimer here, which I guess I won't write, which is that so I'm basically going to assume a bunch of foundations about the Legendrian DGA. So this is sort of similar disclaimer to this stuff that Zach was saying yesterday. I'm happy to talk to you about the foundational assumptions that I'm making and how you can implement them using virtual fundamental cycle foundational technology. So, but that is a completely separate talk that would take up a lot more time than I actually have, so I'm not going to discuss that here. Oh, well, I'm just saying that, like, I don't know. I don't know. I think that it's just this thing is sort of related. This thing that I'm going to describe is somehow related to the Raphoucaille category when you have a filling. I mean, maybe there is some connection there. This is not really like a, this is like a real footnote. It's just a remark about something that might be an interesting thing to think about. But I'm not going to say anything about this. So, okay, so yeah, cool. All right, so now let me start talking about the contact DGA. So, Legendrian DGA. Okay, so so first, let's say I have a pair of a closed contact manifold and a closed spun Legendrian. So that means I fixed a spin structure in the Legendrian. There's various degrees to which you can weaken that, but I'm not going to talk about. I'm just going to assume that I have a spin structure. Okay, so pick. So then to set up this thing, you need to pick a bunch of floor. You basically need to pick a bunch of data to define your floor theory. So let's say I pick a non-degenerate contact form, alpha, and this is with respect to this lambda and y. So what I mean by this is that the ray orbits are non-degenerate, meaning the linearization of the return map doesn't have one as an eigenvalue, and then then sort of a similar condition for the ray chords of the Legendrian. Okay, and I'm also fixing a complex structure J on Xi, and sort of regularization data. So this depends on what kind of technology you're using for the foundations, but this, of course, so this depends on what foundations you're using. But this is just whatever, these extraneous choices that you would choose if you were using Pardon's VFC stuff, or polyfold, like a perturbation of the polyfold section if you were using that. Okay, and then, so now in this, so with that setup, let me fix some notation. And these are going to be kind of the basic algebraic objects. So, okay, so first I'll denote by C of y, sort of the free Q vector space spanned by the good. So if you don't know what this word means, don't worry about it. It's not really going to be very important. So the Q vector space spanned by the closed ray orbits, good closed ray orbits of y. And this is a graded vector space. So it's graded by a version of the Conley-Zander index. And I'm only going to talk about, I'm only going to assume the mod 2 grading, although sometimes that can be improved. And then also, I'm going to note by C of lambda the analogous kind of vector space generated by the Rabe chords from lambda to lambda. And these also have a Z2 grading, coming from some version of the Maslov class, or Maslov number. Okay. And then, so then I have two algebras that I can associate to these vector spaces. So one of them is just the free graded symmetric algebra generated by this C of y. So this is the free or graded commutative algebra. Generated by C of y. And I will try to enlarge my handwriting again on the next board. These are kind of like footnotes. So, and then I can also associate sort of a non-commutative extension of this thing, which is just the kind of A of y, or this graded symmetric algebra of C of y tensored with over Q the free tensor algebra. So, or in other words, the free associative algebra generated by the chord part of the chord vector space. Okay, so this is the free tensor. Get away the camera. Free tensor algebra. Okay. All right. So now, okay. So what is contact homology or the Legendrian DGA or the contact DGA give you? So okay. So the contact DGA and the Legendrian DGA, which are kind of introduced by Ellie Ashberg, Giventhal, Hofer, or at least discussed in their kind of SFT paper, is so it gives you a differential on these two algebras, so which I'll just denote d sub j. And so yeah, so these are differentials. On these graded algebras. And they're computed by signed counts of J-curves. Okay, and what do the J-curves look like? So, so for the contact homology, so for A of y, which is called the contact homology algebra, the differential is counting holomorphic pairs of pants with one input and one output in y cross r. So this is the plus infinity part, and this is the negative infinity part. So maybe this is our starting orbit, and this is our ending orbit. This is our holomorphic curve. And this is for any of the generators, the generator orbits in this vector space. And you have to quotient by a bunch of stuff. So you quotient by this like R translation, and by the reparameterization. And there's also some combinatorial factors coming from marked points and stuff. But anyway, this is roughly the pictures. You're counting curves that look like that. And then for the, so this is how you define the differential on A of y. So for the Legendrian algebra, which is this extension of A of y, so to define the differential on this thing, you like take the differential from A of y on this part, and then for the tensor algebra part, so meaning for a given chord, you define the differential by taking the kind of symplectization of Legendrian. So you take Legendrian cross R inside of y cross R. And you look at basically kind of the similar picture, except now with something with boundaries. So you sort of look at so punctured disks with one input and some number of boundary outputs. And then, in addition, a couple of potential kind of orbit outputs, like this. So this is the input chord, and then we have like some output chords, some output orbits. Yeah, and then you quotient by the same kind of stuff. There's no marked points on the chord part, so you don't have to quotient by that. What's up? It's kind of like a half, yeah, I mean, if you want to think about it that way, it's like you cut a pair of pants in half and then, I mean, it's significantly different, so there's a couple of things to observe that kind of come from the geometry of the situation. So for instance, here the outputs have a preferred ordering, so it makes sense that here you're using the free associative algebra and not the commutative one, because there's like a difference between the things that will end on the chords in one order versus the other order. Another thing is that from this picture, you can sort of, so this picture, you can kind of see that this part, the A of y, is a subalgebra of the E of y part. So this is not just an extension as an algebra, but also an extension as a DGA, because this differential only kind of it'll just spit stuff into this part of the algebra, but not necessarily, nothing goes the other way. Okay. Okay, so there's a similar, where's the eraser? So a similar construction yields cobordism maps. And I will not talk about these really much, but they're pretty important for what I'm going to say. So so here the picture is that if I have like a cobordism between two, so I have kind of a cobordism between two different pairs. So here I have like a lambda plus and like a y plus and a lambda minus and a y minus. Sorry, things are small again. And I have like a Lagrangian cobordism sort of inside of some bigger symplectic cobordism. And let's assume both of these things are exact. So this whole thing is exact. Then a similar construction will associate to this a map of the corresponding algebra, so maps of the corresponding algebras. So I get a map from like the y plus algebra to the y minus algebra, and a map from the y plus lambda plus algebra to the y minus lambda minus algebra. And these are induced by x and by this pair XL. And crucially, these kind of things are functorial up to homotopy, which is the usual thing. Okay, so all right, so that's a really extremely fast introduction and sketchy introduction to the Legendrian DGA. So okay, so the the homology of the DGA itself is not very helpful in real life situations. So one really useful trick, which turns out to have a nice geometric interpretation, is to pick augmentations and then take linearized homology. So augmentations are some really important thing in studying this DGA. So okay, so an augmentation, or rather. So augmentations on A of y or on one of these Legendrian algebras are just unidal DGA maps. Okay, so Q has zero differential, trivial grading, whatever. Okay, so an example? So the fundamental example of where augmentations come from in nature, in this kind of setup, is in a situation where I have a filling. So if I have a situation where I have like a contact manifold and then like a Legendrian inside of it, and then I have like a filling of this thing by like some basically Liouville x, and then also some exact Lagrangian inside of x. Then this thing, by that kind of this functoriality thing, gives me some sort of augmentation associated to that setup. So it gives me an augmentation associated to the symplectic manifold, and also which goes onto the contact DGA, and also an augmentation associated to the Lagrangian on the Legendrian part. Okay, so. Great, good. I'm doing great on time. Okay, so that's basically what I'm going to say about Legendrian DGA, and now I'm going to start talking about how you get these A infinity operations. So before I move on, are there any questions? So I know this is really sketchy, so I'm sorry if this is a little bit. Okay, cool. Great. So, okay, I really like this part of my talk, so hopefully you guys will like it also. All right. Okay, so label this infinity operations. Okay, so now I want to start with the Legendrian DGA, and I want to get to some sort of A infinity structure on something, right? So, okay, so what is the usual thing that an A infinity category, the kinds of things that A infinity categories or A infinity algebras count well? So we will kind of want to get to some count of holomorphic curves which look something like this, right? Like they should have some number of inputs. They should have some, multiples inputs. They should be some sort of punctured disk count with multiple inputs and one output, right? So this is the kind of thing that you would count. You would ordinarily count in this situation. So this is our So this is kind of our objective picture. We want to get to this picture. Okay, so what we're given, and I will just what I will start with is just what I said before. So I start out with this algebra associated to the Legendrian, which I'm going to expand. I'm just going to write the whole thing out as this kind of graded symmetric tensored with free associative thing. And then it has a differential, and I'm also equipping it with some augmentation that I'm going to choose initially. Okay, and the holomorphic curves, again, just to draw a little cartoon, are these guys. Okay, so the first thing that I'm going to do is I'm going to modify, and my writing has gotten too small. It's really hard for me to not do this. Okay, so is to modify the differential to a new differential, okay, by conjugating by some change of basis determined by the augmentation. So, okay, and the change of basis here, so this is like some DGA map of the DGA to itself, and what I'm doing here is I'm just taking my one of my generators. So X can either be an orbit. So X is either an orbit or a chord. And then I am subtracting the value of the augmentation on that generator. So, okay. So basically the effect of this is that I'm like kind of uncurving this algebra. So I'm basically taking it and I'm eliminating all the constant terms in the, by doing this change of basis, I'm essentially eliminating all the constant terms in the differentials of any particular generator. So the resulting thing is I've kind of written down a new, the same underlying algebra with some new differential, and now equipped with some kind of zero augmentation. So basically an augmentation where every generator is sent to zero under the augmentation. So this is and on the curve side, what this looks like, so the picture that you should have in mind of what's going on the curve side is that now what I've done is I've taken kind of the curve count that I had before, or all the holomorphic curves that I had before, and I'm sort of recounting them by plugging various outputs of the holomorphic curves with basically the value of the augmentation at that output. And so it's kind of like I'm like virtually capping off. So I mean, I think a good picture to have in mind is that you're kind of virtually capping off you're kind of like virtually capping off these outputs by holomorphic planes or holomorphic disks with one input. So even though this isn't really, there's no real holomorphic curve here, it's like nice to think about there being a holomorphic curve there. Okay, so the next thing you do, so the next thing I'm going to do is I'm going to take, so I'm going to quotient by the orbit ideal. So there's an ideal inside of this algebra, which is the right, like the kind of two-sided ideal generated by the orbits. So because of the adjustment that I made to the differential, this is now a DG ideal, so I can quotient by it and get a differential on the quotient. And the quotient, of course, by the this ideal is just, you can just check that it's the same as the tensor, this sort of free associative algebra generated by the chords. So the effect of this quotient is that, draw a bigger arrow here, is that now I've basically passed to a situation where I'm looking at the free tensor algebra generated by the chords with some differential induced by the quotient. And now I'm going to still write the augmentation there. And so on the holomorphic curve side, essentially this is having the effect of me forgetting. So now I've essentially forgotten these sort of pants holomorphic curves, and I'm only counting the ones that are kind of disk-like with one input. And all of those disk-like guys now have kind of capped off orbit output. So when I take this part of the differential sort of that I get on this quotient won't have any orbit outputs. Okay, so then what is the next thing I do? So now I kind of want to like flip this thing over. So I will do exactly that. So the next thing I do is I dualize. Okay, so so there's a little bit of a subtlety here in the sense that I'm kind of not dualizing the whole vector space, but I'm dualizing the generators and then kind of inducing a differential in that. But this is, you can check that this is actually a valid thing to do. So basically, I can take the dual vector space, or in this case, it's more convenient to take the dual vector space and shift so take the dual vector space of the chord vector space and shift it by 1. And I can take the free tensor coalgebra generated by that. This is now I should now think of this as a coalgebra. This is so small, okay. And yeah, and this, now I have a new differential on this, on this thing. Okay, oh, and also maybe I should, I should shift this now. I'm not being very careful with the signs because it's Z2. Okay, so now basically the resulting thing, so now the new differential is sort of kind of the, some sort of opposite differential. So now if I'm visualizing the holomorphic curves that are being counted, the kind of curve is sort of flipped like this. And now, so now the last part, so this is the part where you actually get to the final infinity algebra part. Okay, so now that I have this tensor algebra thing, so there is an operation. So essentially, if you kind of look into one way of defining infinity algebras, one way of doing it is by basically taking the, if I have a vector space and I want to define an infinity structure on it, then one thing I can do is I can take the free tensor coalgebra generated by the vector space, shifted by something, and then I can define a differential on that is a coalgebra differential, and it turns out that this is equivalent to an infinity structure. This is called the bar construction. So, so what I can do now is I can debar, which means just kind of reversing the bar construction. And in particular, what that means is that I can define these infinity operations by taking the projection down to the first part of the vector space of the differential restricted to a particular kind of the kth tensor power. So let's see, check tensor k. Anyway, so that's kind of formally what you're doing. And then there might be a sign here that I'm forgetting. So there's potentially a sign, which I didn't check beforehand. But anyway, so this resulting projection gives you an operation from kind of the kth tensor power, which is like the kth piece of this thing, to the actual vector space itself. And yeah, so one can check that this actually results in an infinity algebra structure. And sort of on the curve side, you can see that essentially what we've got here is exactly the thing we were looking for to get an infinity operation. In particular, we've like capped off all of these pieces and we've turned over we've turned the curve over, right? So the resulting, so like this picture is essentially this picture modulo kind of forgetting that these caps are there. Yeah?
So this is really defined on the dual of C lambda that's uncountable dimensional?
Yeah, so this is a really good point, and one of the reasons why, I mean, it's a disclaimer that I probably would like to put on this, which is that Yeah, so these vector spaces will end up being the dual of something that is potentially countable, so that is not great. On the other hand, I mean, I think that if it's uncountable, then you're kind of in a good situation from the dynamics perspective of things, so I don't know. But yeah, I mean, there's also, so there's an alternate version of this, which is much more sophisticated, that you can define using rational SFT, which is not dual, which involves no duals. But it's much more complicated to talk about, so I'm not going to talk about it. But that is a great observation. Thank you. Okay. So so that is the discussion of these A-infinity operations. Whoop. Terrible erasing. Okay. So now, so far I've only talked about things with one Legendrian, so let me talk about what happens when you have a Legendrian link. Okay? I'm only going to make a few remarks that will basically make it clear kind of how what needs to be said about that. So in like this Ng paper, or Lenny's paper with everybody, this is called a link grading, but I think an object grading is also a good name for it. Okay, so now suppose that I have some Legendrian links. So I have like a union of a bunch of Legendrians which are all connected and compact. Okay, so then, so first statement is that if I have a bunch of augmentations on, I have a bunch of augmentations epsilon I on lambda I. So if I have a bunch of augmentations on the pieces, then this induces a diagonal augmentation on the union. Basically, the reason for that is that if you had constant, so like if you have a chord which has constant terms in the differential, then it has to be on the same connected component, like the two chords that, or that chord has to be connecting a component to itself. So essentially, you don't really need to add anything if you want to augment the union of the link. So then this dualized guy decomposes as into a bunch of pieces which correspond to the different components, which I'll denote like this. So this is the span. So this is equal to the span of the chords from lambda I to lambda j. The dual of this shifted, and then the mu k operations respect this decomposition. So what I mean by that is that essentially, if you have so if I look at the mu k operation and I'm looking at kind of a sequence of these chord spaces, then maybe I'll just write it up really quick because it's actually more complicated to say. Okay, it's not going to fit. I wanted it to fit on the bottom of this, but it's not going to happen. So what I mean by this is that if I have a mu k operation and I'm looking at it on kind of a component like this, tensor c check lambda, let's say k minus 1 to lambda k prime, going to c check mu 0 lambda k. So maybe I'll write this convention. I may have screwed up. I've confused myself with the order here. But roughly the idea is that if you have a composition of this form, then and you have kind of going between components, then this composition can only be 0 if each of the endpoint Legendrians for each of these guys matches up. So basically, lambda prime I needs to be equal to lambda I for all I. So basically, if the infinity operation is not 0, then this kind of setup has to be composable. So that's an important, a very crucial way that this thing respects the link grading. Okay. Didn't shift this, whatever. All right. Okay, so that sets up the A infinity operation. So unfortunately, kind of the most naive thing you could do, where you define the HOMs by just using these vector spaces, is not the right thing to do. So the reason it's not the right thing to do is because essentially the thing you get in the end will not be fully isotopy invariant. And this is very bad for a lot of, this is like very, very bad for lots of reasons. So if you try to naively define the HOM spaces like this, you'll run into a lot of issues. So so to fix this, we are basically going to now kind of transition to the GPS part of this discussion. So yeah, let me erase this. Okay, so now we're kind of entering. So now we're going to basically take this. We can take this kind of setup and create, kind of produce some analog of the self-floor homology of a particular object. So in this case, it's this kind of the self-floor homology of an augmentation. So we could get some homology group associated to an augmentation. So as so. So, and this kind of thing is pretty like kind of the standard thing you do when you set up the floor homology of a Lagrangian. You just have to be careful with the augmentations. So, okay, so you pick a small push-off, lambda prime, of the augmentation that you're interested in. And you give it an augmentation which essentially pulls back under some trace isotopy to the original augmentation that you had. So what that means is that you pushed off so you had lambda and you like pushed it off by a little, by a small isotopy. And the trace of that isotopy gives you some Lagrangian cobordism in the symplectization between those two things. So you can pull back, you want these augmentations to be consistent in the sense that the augmentation on the original guy is the pullback of this augmentation. On some augmentation on here. Okay, and then, so now to define the HOM spaces, or define the algebra complex, so this homology algebra of the augmentation is just the homology, the cohomology of this, of the kind of, this graded part of this sort of dual DGA of the link. And where we equipped the original DGA with the diagonal augmentation. So we were using this diagonal augmentation on the link lambda union lambda prime. Okay, so, and composition is defined. So here, composition is defined similarly by basically taking two push-offs and then defining it using that. Okay. So, so obviously an important thing is that, so an important claim here, I mean, this is kind of the crucial thing, is that this HA, this algebra is unital and invariant, independent of this push-off, and also kind of up to a non-canonical isomorphism, sort of homotopy classes, or homotopy invariant under homotopy. of augmentation. So, basically this algebra is kind of invariant under under alterations of these choices in the way that you would want. Okay, and so the invariance part kind of follows. So a lot of this, basically everything I've said has been kind of formal thing that will follow formally from the setup of the Legendrian DGA, but the unitality of this is not. So the unitality is like a thing which you actually have to prove, and you kind of have to go under the hood to do it. Complicated. And so, so the way that I'm writing about this in the paper is that you can do this by adapting a construction of continuation maps in either Baron Cornea or Jeff Hicks. So Jeff sort of implements this construction in his thesis, so it's really useful. He was very useful to talk to for this. And I'm happy to elaborate on this, but I'm not going to talk about it now because it's really pretty technical. But so the picture of the unit, which I will now draw, and this is an extremely useful picture to have in mind in general for this kind of thing. Okay, so what I had before is I had lambda, and I had like a push-off of lambda, right? And so in the setup, there's kind of three kinds of chords that you'll get in this picture. So one kind of chord is like a short chord. So this is a short chord going from lambda to lambda prime, and these are basically coming from the tiny. This is like these things live in a kind of more spot family that's just corresponding to the original Legendrian itself, right? So this is like what happens if you rate flow the Legendrian forward a little bit. The other thing you'll get is kind of the long chords. So these are the chords that come from from lambda to lambda prime, which come from the original chords of lambda itself. So these are long chords. And then the last kind of chord, which is not actually in C check lambda to lambda prime, but will be important later in a little bit, are kind of these backwards chords, which also come from lambda and which are going from lambda prime to lambda. So these are the ones that basically are inherited from lambda prime from the original self chords, or inherited by lambda prime from the original self chords of lambda. So these are kind of the backwards chords. So okay, so so the short chords and the long chords are the generators of this guy. And so so from this picture, you can see that inside of HA, at least the complex of HA, there lives kind of a copy of the cohomology of the Legendrian, and that inside of that, there's a unit. And that is the unit that you were looking for. So that basically is going to be, assuming, under some assumptions, you have to make some assumptions about what you did exactly with lambda prime, but that's essentially where the unit is coming from. Okay. No. Okay, so I should really emphasize this. These are not, I said this in passing, but these are not not yet. So these are not in the HA of epsilon lambda, right? What's up? Oh, okay. Good. Yeah. Okay. So give me a second. Yeah. Okay. So I'm not going to say anything about that, but that's an interesting observation. Okay. So now the last thing I'm going to say, which will be kind of related to that comment, I think, is. Okay, or hopefully not the last thing I'm going to say. So now you can get a category. So now to get the actual category, I basically apply this localization procedure of GPS or of Abaziad-Seidel. So Abaziad-Seidel are actually the people who invented it. So GPS are just, they just have a nice short explanation of it. So see, for instance, GPS. Okay, so basically to get, so the point is that to get the actual category, we have to wrap. So what we do, so one way of explaining how this works is you pick, so this is basically how they do the wrapping in GPS, although in the actual thing, if I were to actually treat it here, it would be a little more sophisticated than this. But basically what you do is you pick a bunch of objects, so a bunch of pairs of Legendrian augmentations to span the desired subcategory, some desired subcategory that you want to construct. And you pick a sequence or some positive isotopy starting at, for each Legendrian. So this is lambda I. So you pick some positive isotopy of Legendrians, which so that are basically, and then you kind of take the constant, you take sort of each of the, for each of the, integer times, you take the push off given to you by the positive isotopy. So you get like a z plus many of these, and you also have to do this in a way, of course, that's consistent with the augmentation. So it's a little bit technical to say what that means, but you have to do that part. And then you define this thing called category O. So this thing has it's an infinity category with whose objects with objects. So the objects of this category are the elements of the sequence, or all the elements of the sequence, so for every I and j. And then Hom between two elements of the sequence, basically, so the point is that Hom between the, so to define Hom in this category, you basically say that it's 0 if, kind of lambda j, if this element happens before this one in the integer sequence. So it's 0 if this happens. It's z if, or I guess if j is equal to I and k is not equal to L, that's not really that important. So it's q if ki is equal to, let's say ij is equal to kl. So that means if they're the same, if they represent the same, literally the same Legendrian, then you just define it to be the base field. And then if they're sort of in front of each other, then you define the thing to be this. Let me say ij kl. And so basically what you do is you kind of define a directed, to define category O, you define this sort of directed category where you're only allowed to take the correct Hom between two things if the thing that you're taking Hom to is like in front of the thing that you're taking Hom from. And then you so there's a procedure called localization which allows you to localize essentially at the image of at some kind of some set of morphisms in the homology category. In particular, we have continuation morphisms coming from the unit of this algebra. So we can localize at continuation elements to get, and so the resulting thing is exactly the category we're looking for. Really, the category that's kind of spanned by the really the subcategory spanned by this thing, but that's fine. So this is the localization of this guy at the continuation element. So this is obviously really sketchy because I'm running out of time, but yeah, I mean, roughly speaking, the thing you want to get to get the unitary category in the end is just implement this wrapping procedure like you would in regular floor theory. And yeah, so now, interesting observation is that the resulting thing does actually include the backwards chords now, at least kind of morally. Because essentially what you've done is you've, on the level of homology, you're sort of taking a colimit over all positive isotopies. So you're essentially, for at least the Hom of an object with itself, you're essentially taking this you're taking the homology of this this kind of pair complex, and then taking lambda prime to be extremely, extremely far away. And in that limit, each of these backwards chords starts to appear, right, in the complex. So, so even though the backwards chords are not present in the original guy, they sort of start in this kind of the same way that they start appearing in wrapped Floer homology. They begin to show up as you take the kind of colimit involved in computing the homology from this. Okay, so I have like 3 minutes, so maybe I will take just 4 or something to discuss. Okay, so now I'm going to discuss this dynamical stuff. So I'm going to give you some really, really basic examples of how interesting dynamical facts about the contact manifold could be stated in terms of the category. Yes. Oh, yes. Okay. Can I do it after? Can it be a question? Okay, great. That's a good question. Okay. So let me talk about some dynamic stuff. So all of this stuff will be happening at the level of the homology, so you could probably state it without the category, but it's an interesting context to say this stuff in. Okay, so here's a lemma. So if lambda is a Legendrian with no Rabe chords, then, so first lambda admits one augmentation up to homotopy. I really have not said anything about augmentation homotopies, but this is some natural equivalence relation. So first lambda admits an augmentation, one augmentation up to homotopy. And then also the self-hom of that augmentation, the endomorphisms of that augmentation are quasi-isomorphic to the Morse complex. This is entirely obvious from this picture, because basically what this is saying is that suppose lambda didn't have any Rabe chords to begin with. Take the positive wrapping, which is given by the Rabe flow. There are no backwards chords and there's no forwards chords. There's only these chords. So when you do this localization, it's essentially not going to change the original homology group. And when you're very, very close to the original Legendrian, the chords live in a Morse spot family, and they're just in bijection with lambda. So this is kind of the chain, kind of just on the level of the chain complex. And then I think you could probably upgrade this to a statement about the infinity algebras. Okay. So on the other hand, okay, so corollary of this is that when this category is 0, then this implies the Cord conjecture for all Legendrians. So I should really say like sort of transverse Legendrians in the category. So what I mean by that is that if the category is 0, then no object can satisfy this, right? So that means that the thing that every object in there has to satisfy the Cord conjecture. And actually, you can prove something much stronger, which so this kind of picture can be upgraded to some exact sequence relating the linearized homology to the linearized homology, the homology of lambda, some sort of dual linearized homology to the homology of the self-hom of this augmentation. So using that thing, I mean, you can essentially adapt this argument in this Ekholm paper by Ekholm and some other people who I'm sadly forgetting, where they prove basically that this there's actually an effective lower bound on the number of chords by kind of half the sum of the Beatty numbers of the Legendrian. So this thing actually implies something much stronger than that. So an example of a situation where this is satisfied is the sphere. So that's a really stupid example. But there is much more interesting. You can get much more interesting classes of examples by basically examining contact manifolds where any Legendrian can be displaced from the Rabe flow of an isotopic copy of itself, any Legendrian emits an isotopic Legendrian whose whole Rabe flow is sort of disjoint from the original Legendrian, and also you can go even further and implement that argument for something which has that property in some way, in some action asymptotic way. And so that actually opens you up to a big class of contact manifolds. I believe you can actually implement this argument for subcritically fillable things, for instance. So that's a big interesting class of stuff. But I don't have time to discuss the details of that. So I'm gonna finish my talk there.